Okay, hello everyone. Please take a seat. It is my great pleasure to introduce to you our keynote speaker, Michal Valko. Michal received his PhD in 2011 from the University of Pittsburgh under the supervision of Miłosz Hauskert, and was a postdoc of Remy Munoz before getting a permanent position at INRIA in 2012 and later starting at DeepMind Paris in 2018. Currently, Michal is the principal Llama engineer at Meta. He is primarily interested in designing algorithms that would require as little human supervision as possible. This is why he is working on methods and settings that are able to deal with minimal feedback, such as deep reinforcement learning, bandit algorithms, self-supervised learning, or self-play. Michal has recently worked on representation learning, word models, and deep learning algorithms that have some theoretical underpinning. In the past, he has also worked on sequential algorithm with structured decisions where exploring the structure leads to probably faster learning. Michal is now working on large language models, in particular providing algorithmic solutions for their scalable fine-tuning and alignment. Michal, the floor is yours.
Thank you, thank you. Hello everyone, glad to be here. So last year in November, on my birthday, I received a message, and it was not happy birthday. It was like, oh, I'm Oscar, you know, I have this conference, and like, and I have a friend Mateusz, and can you come and give a better talk than him? And it's like, I was like, it's not a competition, you know, like, I can come. And then I said, okay, well, so I prepared this talk on like, you know, road to AGI with very beautiful videos and you know, how to actually show that stuff that Timo and Piotr are doing, it's not the way to go, and you should not do contrastive learning, and the non-contrastive learning is better, and it saves the planet because it's more ecological. And so it was all ready, and then in January, like Oscar said, well, no, don't say that. I want you to talk on training Gemini because I want to have better conference at ML And so I said, okay, well, he's the boss, right? I guess I need to change the talk. And so like I prepared something else that will be on the topic. And then, of course, I had to come to Poznan because my dear friend Wojtek lives here for 45 years. Oops, I said his age. Yes, well, yeah. Yes, I should be more formal, right? Like I learned that I need to address him as doktor, habilitowany inżynier, profesor Politechniki Poznańskiej, Wojciech Kozłowski. This is not the beginning. All right, so I need to click on this. Or maybe I can do, oh, thank you very much. Yes, thank you very much. Yes, all right. Okay, so this is Poznan, this is me. This is work of a lot of people that I was happy to work with. And I still want to discuss that, you know, we're on like kind of in the project of, you know, making, you know, AI useful, you know, making it scalable, making it learn, you know, to benefit a lot of people. And if we want to do something that people would use, we cannot ask them to spend a lot of time, you know, labeling the data and providing extra information, right? We would like something that will be useful from the beginning, right? So we would like to have algorithms that require this minimal feedback, and so that's why, like, you know, as Mateusz says, I've been working a lot on things that require as minimal feedback as possible, right? You would like to learn from what you observe because, you know, that's how the kids learn, and you know, self-supervised learning, and you know, transformers are also the ways of training, you know, predicting what you already know, right? And today we will talk about large language model and actually how to actually make them more aligned to human preferences. I know I have like 15 minutes at the end for questions, but I would prefer questions anytime, so I don't need to go over my slide, just shout and I'll I'll just try to answer if I can. And I know I'm between you and lunch, so I'll not speak be after 1:30. Yes, so I will talk about algorithm alignment, why and how we improved it in the training, and actually, the math that was behind it, because we're still in the, Polytechnic University, and so it should not be only about pretty pictures. All right, so there were a lot of talks on large language models, and so I will just assume that everybody knows how they're trained, and if not, let's have lunch together and discuss it over that. There just mentioned that there are kind of these 3 phases that we usually do, right? Like pre-training, when you take billions or trillions these days of tokens and try to, predict that next word. Then we have something that's called instruction fine-tuning, because here, after that that phase, the transformers only complete the sentence, but it's not, it's not a conversational. It's just a next word or next token prediction. But then we want it to, make it kind of conversational. So we want to make it follow instruction and respond to our questions. So for that part, we use the instruction fine-tuning. But since the transformers are usually and LLMs are trained on all internet, including Reddit and Twitter, the time things can come out of it after this phase are not very nice, and we don't want, large language models to, to swear at you, provide financial advice, be sexist, racist, and all of these things. So we would like, them to be useful, but also kind of, as we call, aligned with human preferences and safe. And so this is what I spent last 1 or 2 years doing, kind of trying to make them safer, and particularly with a specific algorithm, how to make it safer faster, how to require as minimal input from people, because that also takes time and money. And I have 45 minutes. Good. All right. Any questions already? Because I'll just assume that all knowledge of LLM training is done. Good. Everybody knows. All right. So I'll try to first convince you, as I had to convince people also in DeepMind, why we should do things potentially differently as ChatGPT was trained, and why could be potentially a better way to train things with slight modifications, right? And so ChatGPT and other models are trained, or part of this alignment thing is that we train this reward model. So maybe I should kind of introduce things a little bit, right? So after this second phase of supervised fine-tuning, we get LLMs, that's partially harmful, and then in this, and then in the next phase, we want to have this updated version of it, and then we look for another LLM that users would prefer to the original, right? So we have this potentially harmful SFT LLM, and we find another one. Yes, maybe I can use this microphone. It doesn't work. No, it doesn't. Oh yeah, maybe I can. Yes, just so I can use my hands a bit. So we would like to find another LLM that is better than this one, right? And so for that we need to ask people, between the two ones, which one you prefer, and then you try to make it happen more likely, right? So this is kind of general picture what we're trying to do. We have some MLM just kind of trained on internet, and some other completions that human provided that we have to pay for, and then we want to improve it, finding one that's potentially helpful, less harmful, maybe even better if we can, right? So this is kind of the main scenario, and for that we usually we cannot ask a lot of people to give us preferences to all possible completions, because there are many. So we have very few. We train something we usually call a reward model to generalize. So we take tens or 100,000 of human annotations that do you prefer this one or this one, and using this X, so this is the prompt, the input and output, we trained this kind of reward model by some kind of ELO score. So this is the same thing as a chess. Would you prefer this one? So you kind of have two different completion fighting for each other. For this question, is this answer better or this one? And which one wins? And that's what we're kind of doing, and we just use same scoring as in chess. That's why it's called ELO score. And so that's what we're trying to do. And once we have this reward model, they said, well, we train some neural network that can then generalize for any possible question and any possible answer. And once we said, well, now we don't need people anymore. And then we just try to use this reward model to do many, many, many more steps of training. Right? Is that clear? So this is how like ChatGPT is fine-tuned. And the process of this is called reinforcement learning, because we reinforce likelihood that the things that come from new LLM is better. Well, and so now I'm going to tell you why this is wrong, or not the best, right? Because in general, when we have one policy, one LLM, one language model, and we will find one is the best one, well, okay, we found something that's better than this one. But maybe there is something better than this one. And maybe there is something better than this one. So in general, you would not like to be just better than one particular one. You would just not like to, in chess, you don't want to, beat your, 20-year-old younger brother or whatever, right? You want to be better than everybody, right? You would like to have LLM or chatbot that humans prefer to all other chatbots possible, not to one particular one, right? So, this is kind of this is something that they will try to see. Well, I think this is quite evident. This is a better objective. And now we're going to talk like how to achieve this objective. And so first step, we kind of change the way how we will train this reward model. Yes, they told me, Mitra told me I need to stand here because it looks better on the camera. So I'll try to follow the advice, follow the instruction. And so for that, we will need to see how actually we train this model differently. So instead of saying, oh, for this prompt, for this question, and this completion, this is the score, we will give it both of the options. Okay, well, this is the prompt, this is one potential answer, this is a second potential answer, and we will just say, well, which one, we will train neural network to predict which one they prefer. So there'll be number between 0 and 1, very simple. Here with some L scores, will be some numbers like in chess, and here will be just preference, right? Well, we don't do any score. Yes, and so particle function, how we train is this one. This is you're assuming some specificity of this L score because still it's a model, it's some assumption how things work. And the way to train is the simplest one-on-one supervised learning, right? We initialize LM with this prompt, given this prompt and the response is, which one of things do you prefer? And then we train it using supervised learning. Nothing miraculous. This is how we train the reward model. So now, once we have this reward model, I'll try to convince you that working with this reward model, it's better than working with this ELO score chess-based reward model. So less assumption. So what we would like to see about this model. So we will not assume anything, right? That's kind of like my question. Why we assume that things in a large language model work like chess? There's not really reason to. And so we'll just assume that only thing that we need for reward model that is anti-symmetric. So if you prefer something, A to B, 80%, then B to A, you prefer 20%. Thing to believe. So this is just this. And so one part, so we'll say, okay, this is kind of the scoring rule that we will assume the thing, and then you can see that, well, you have for this prompt and this one, if we sample here random humans from the 8 billion people on the planet distribution, then this particular person would prefer this response to this one, and then we take expectation over all possible humans on the planet. Let's assume we care for humans on the planet and not like aliens, like Ahmed says, and maybe we'll need to sample from aliens too later. And then we'll just say, well, one thing that we could optimize is like, now once we can have the preference between, one completion versus other, then we said, well, then let's prefer like one LLM, like, I don't know, the, GPT-4 versus Claude. This way, if we sample one completion from, GPT-4 and one from Claude, this is how I would prefer answer for this one versus this one, right? So it was just a definition. So we can have a preference between two completions given the prompt, and then we can have what would come from different chatbots, different models. Good. So this is simple. And now we'll try to see why we should care about different objective and try to convince you that these objectives are already different, because it's not really evident that they are different. So we can define something's probability to winning, so that we have in previous slide. And now, this is what I tried to explain. I would like to have my chatbot better than every possible other chatbot. So this is a new thing. This is, John Nash definition of equilibrium, from the movie Beautiful Soul or something. I forgot. Yeah, that John Nash from 1960s defined something like Nash equilibrium. Like, I would like to have, best possible chatbot. So if I'm looking for best chatbot that if I compare it to, any other chatbot possible, it will be better, right? So I want to find the maximal chatbot that for any other chatbot, my chatbot, it's better than this one. This could be the, same kind of, this could be, Llama 3 with different weights, which, like, this is something, or like Gemini 7 with different weights compared to something else. But it doesn't matter, it could be any possible answer. It doesn't even need to be even deep network. I just want something, so this is kind of very important, because this is what we'll strive. The whole talk is on how to get it. So like, it's kind of important that you believe this is a good thing. And if you don't, please ask me now or leave. I don't know. Because it will be not very useful to know how. Good? All right. So if we agree we want to get there, then we'll try to see why this is like a maybe better objective, and why, assuming kind of general preference model without any assumption is better. So the thing that's used in chess has like a very formal name. Elo is the name of the person, right, that did the scoring, right? There's a formal name called Bradley-Terry model. So we said, like, probability of preferring one to another is like a sigmoid function of, like, Elo score of 1 minus Elo score of second one. And so let's even assume that we can actually capture some preferences. So now we have a particular, prom, like which castle is the best castle in Poznań, and we have like 3 possible responses, and then we have like which one we prefer to each other, right? And I just put some numbers that would follow Bradley-Terry model. Some numbers that sum to 1. And it could be captured by Bradley-Terry model. So if, for example, reward for this answer is 0, this one is log 9 or log 2, this is perfectly captured by Bradley-Terry model. And the thing is, if we optimize LLM for like, well, give me the one gives you the best possible chatbot, so like kind of first objective, like the ChatGPT objective, let's say, you get this reward. Like, so it means like always answer with the second option. And if you say, well, if you go for best preference, it's actually also the same. So you say, well, what are you talking about? You change objective, but you get the same answer. So, it's useless. What changes there is because usually we don't train for best possible thing in the large language model, right? We want this kind of safe model, a line model, something that will not tell you how to build weapons or how to, I don't know, find drugs or anything like that. Right, so we usually constrain it to some objective. And so like let's say this is some random constraint that I just created for this, three responses example. If you constrain to exactly the same objective for this kind of, let's say, ChatGPT objective, you get, oh, you should prefer this one with 2/3, this one with 1/3. So 2/3 of the time answer this castle, 2/3 of this is, answer this objective, right? And if you do the other one, you will get always answer with third, so completely different answer. So this is, I'm not saying which one is better, I'm just saying that this is different. These objectives are different, here is just showing the math that, if you do this particular thing, you're the one that, if you optimize for best possible reward, so this is like ChatGPT 2 is doing, you should answer this, this is your reward you get, something better than log 2, but there is one possible chatbot that, according to these preferences, humans prefer even over this one. Slightly over, right? Like 50 over 99. This is like a small, tiny example, just things that if you go for a different objective, you can get something that humans would prefer more. And so this is what we will try to do. And I'll try to keep more convincing, because I think it's more important, like, convince you about the objective, what we're doing, and then talk about the method how. So, one of the things why we want to do that, right, is that we want to have preferences that cater to diverse human populations, right? So let's take some examples, right? Like in US you have like Republican Democrats, and like if you have one data point that is more Republican, then if you train your model according to ELO score or ChatGPT, everything is Republican. And if few more data points come on Democratic side, then everything is Democratic. Maybe you don't want that some majority, whatever it is, wins over. So this is a simple example, but ELO score could be even more particular. Let's say have 160 countries, and then you just have the country that is more populated. Or you have, I don't know, 20 different tastes of ice cream, and one is just one more data point. Everything will be of that one. Like every color will be the same. So then you said like this Bradley-Terry model will select one possible thing deterministically all the time, and stuff that we care about, these Nash preferences, will be mixture of policy. Sometimes like 50% gives you Republican answer, 50% Democratic answer. Maybe this is not what you want, but if you want to cater to diverse human preferences, this is something that we should do. And I have only half an hour, and I talk very slowly, so I'll try to do better. Yes. So another things like the Bradley-Terry model has limited expressivity. For example, Bradley-Terry model, ELO score are transitive. So it means like, if like Wojtek is better than me, and I'm better than Oscar, and Oscar is better than Wojtek, for example, if you play tennis, then Bradley-Terry model cannot capture that. Like, it cannot capture the circle, like A is better, B is better, C is A. So it's impossible to capture. Like, for example, if you have these non-transitive dice, like very old example, there's no answers from rework model that would capture this thing, because it's just restrictive to this. Another one, I'll give an example because we are short of time, and this example I think will be illustrative better. So imagine that I'm from a small village next to Poznan, and I play in my high school, and I'm the best chess player. And I have the biggest ELO score because I win all the games. Well, and then I come to Poznan and I'm no longer a best chess player, right? So my ELO score will change. So ELO score actually depends who you play with. So if I play somebody that I always win, that's what I do, right? Then I have very big ELO score. So that's why in real life this would not happen for chess. Right, because like if you have very ELO score, that they made you to play Kasparov, and then you lose, right, and then your ELO scores go down. But in the what I do, I refuse to play with Kasparov, and I keep my ELO score high. We don't do this, with a large model. We don't, we cannot make every option to be compared to everyone. So that's like that's a problem to have, right? So we don't want something that depends on how we sample the data. We would like to have something that's independent of that. And like the model that we do is independent of that. And the last thing, that convince, people in Google that like this should be the way of training is that fits better, right? If you have some human preferences and you're training, using like reward model, you fit, to this percentage, your reward model. And if you do ones that without this assumption, which we call this preference riddle model, you get better percentage, right? And it just fits better. Why would you use something that fits worse? And the final thing is that this data come in the preference, right? Like the data, the way how we collect the data is like, this is a prompt, this is potential answer A, this is potential answer B. So why we just don't learn how much answer A is preferred to answer B, and why we actually even, try to come up with the ELO score. We're not gaining anything, but we're losing something. It's the same network, takes same time of training, so there is no need. ELO score and Bradley-Terry model have as any model in science, they have a useful, right? Sometimes you want to explain some phenomenon, you have less parameters, so it's used to you modeling. But in this particular LLM examples, we're not gaining anything. So I think we should all just use preference model, and that's what we did. All right, and this is, this was kind of Wade, to this Nash-LM. Now the question is like, well, how do I find such a model that humans would prefer to any other model possible, right? Like, first it's like, what, and now like how to get it. So, this is work of a lot of people, we have the team that actually focus on the, especially this picture of, this is not me when I was younger, this is John Nash in 1960 when he defined Nash equilibrium. And just recap what we're doing, right? Like we will have two phases. First, we already talked about, we train this preference-based model, and then in the second phase, we'll just compute the Nash equilibrium. So we'll have some kind of two policies, and we'll try to improve it to the point that we find chatbot.lm, that one that humans would prefer the other one, right? So like we want to have this is our final LLM that we give to the users, to play with. If they would compare it to any other, it will be better. That's a goal. And so there's actually a story how we came to this algorithm of Nash-LM, and its story is like 10 years old. So it didn't come actually from Nash-LM, and I don't have time to do it, but I can tell you over lunch, or over coffee, over beer, how it happened. So we worked on some problem in the learning theory for a long time on kind of trajectory feedback. So you have like different kind of games like Go and Stratego or a poker that you don't see the cards of other people, and you want to play perfectly using self-play. And so it took a long time to actually put all the pieces together. You need to have like a right algorithm, right estimate, like balancing some magic. So and actually, like it took kind of 10 years to get to the point, right? So like it started, at the beginning. It started in 2014. When I worked on something called implicit exploration, and while there are many other things, many other people go in, like our friend with Wojciech Gergely, he proved that this implicit exploration, converges with high probability. Christian in New York proved that the scalar regularization, the right weighting to Steve. Mark in Canada, different university, proved that like Monte Carlo counterfactual regression minimization is the way to estimate things. There's a lot of other things. Shijin came, a student of Michael Jordan, showed that using implicit exploration and Gergely's proof, you can get, high probability guarantees for that algorithm. And then we also thought we actually solved it in 2021, but we had to look, we had to at least get one search of the whole tree of things. And then so we came back to this. He worked 2-3 years more, and finally, solved this problem for the game theory. We get like some prize in some conference, and then we said, well, actually, this is algorithm that we could use for training large language models to solve large equilibrium, because also here we don't see all the answers, and so an algorithm is actually quite simple. So we even have time to explain it here. So just to, and it's very useful that it's simple, because anything that you do these days in large language models, it has to be simple, it has to scale. So what we're trying to do, recap, ChatGPT and Sparrow and other models were trained, with some algorithms, reinforcement link, called, like PPO or something, and work with this ELO score. And algorithms is also quite simple. It has to be, right? It's just like we try to generate some responses from reward models. We use this reward model to score them. Which one is better? Who would win the game if they play against each other? If we give humans to see which one they prefer, and then we try to make the ones that humans prefer more likely by just grading descent. So and this is like grad log pi, because it's policy grading. Like we call it like LLM is like a policy, like probability you output the next word or next sentence, and we just to improve the one that's higher. There are some details, but it's pretty much it. Like for example, one detail is that usually those things have high variance, and so we reduce the variance by subtracting number that's like it's called value baseline reduction. For example, like if this number is like 101, 102, 104, so here we're going to subtract like 100, and this number will be smaller, so its variance, smaller number, smaller variance, trains better, because deep network don't like if the numbers change fast. This is it. One of the, and the thing is that this value function is tremendously difficult to learn. You know, getting this number 100 right is very difficult because you have one number for all possible, you need to have it right for all possible prompts, and there are infinite many other prompts. So it's very difficult to find which one is this number. It would improve the training, but it's hard to train. We still do it. Well, what beauty of this Nash-LLM that it was unexpected benefit, we get this for free. And why get this for free? Because at the end, you find this best possible policy, best possible chatbot you want to train. So the one that has this Nash equilibrium. When it's Nash policy, they play against each other, they're at equilibrium. So like if you play tennis or chess to yourself. So if you play chess with yourself, who wins? Well, you. But like half of the time, you A and half of the time you B, right? So you have, if you put two equivalent players next to each other, it's 50% chance that first one wins. And so here, what is the baseline? What is like average time that somebody wins? Well, it's 50%. So in Nash-LLM, we don't need to train another trillion parameter network that just to predict one number. We just delete this number and replace it with 1/2. So this is kind of practically useful, and we didn't plan for it. We could say, oh, we were so smart, and like we think about it. No, we just said, well, this is 50%. We just put 50% there, because now before these numbers were ELO scores, right? These rewards, but now these numbers are between 0 and 1. How much you prefer one to each other? Well, and what's like the average of 0 and 1 numbers? So let's go back. So this is what we're trying to find. We try to find this Nash equilibrium, find a chatbot that another chatbot is preferred to any other chatbot possible. And so we use the very simple algorithm for it. It's called mirror descent. It's also, we didn't invent this one either. It's invented by Arkady Nemirovsky in 1970. So see how to study. You need to take Wojtek class, go to school, and then you train Gemini. All right. So and this is what we use. And the question is how actually we practically implement it. Because in the training of like ChatGPT, there is this phenomenon called reward hacking. It's like if you have this reward model and try to maximize it, it will find a way to maximize it. You will get best possible things from reward model, but since it's trained on very little data, it's not very good on the data it didn't see. So by some random chance, it starts to give you very high numbers, preferences for something that doesn't make sense because it didn't see it. And then in the end, you get a chatbot that just puts pizza, 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 pizza to any question. And this is called reward hacking. And so there's ways to address it. And usually ways to address it, we won't say, well, don't go too far, don't change weights too much from the weights that you've already seen, or don't go too far from the data that you've seen. You don't get as high rewards, but you do get pizza, pizza, pizza. I mean, if you won't get pizza, 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 then there's simplest way to get it. So now, we didn't address reward hacking using Nash-LLM. Like, we still have this problem. If you are for data, you don't know what to do, right? There is no magic there. But there is actually a nice way how you can somehow address it here. So from this trained reward model, well, you get some number between 0 and 1. And now say, well, could I use it also for other data, right? So I'll try to use the microphone again. So you will look for one chatbot that's better than every chatbot possible, right? So I put this thing, like imagine like this is the space of all weights. Each point in this space is like all trillion numbers of weights in all network, right? So we have one chatbot that we started, and ChatGPT found one that's better than this one. And now we want to find something that it's preferred to all other possible, right? And now the thing is like, well, we cannot really try them all, because the ones that are really far, we cannot evaluate how good it is, because our data, people are only here. And people there didn't come to the talk, so they didn't evaluate our model. And so what we do, we all say, well, only look for weight in this auditorium. And so one way to get it, you can say, I constrain my search, my gradient descent with respect to this one. But this is actually, well, in constraint optimization, sometimes more difficult to do. So we did something, you can call it a hack, even simpler. What we did is, we said, well, we'll trust those things that are far away dataless. So, and this is how we do it. So we get this number between 0 and 1, how much you prefer one towards other. And then you say, well, look, this is the chatbot with this kind of data. And if the data is too far, so if the model weights are too far from the ones that you start with from this SFT, from the second phase, then penalize it. Like, don't take this number into account, right? Like, so it's like, oh, I found weights, they're so much better than these ones. But if it's far from our data, we said, well, yeah, it's far, but you know, I discount it. I subtract the distance, how much you're from the data. So either you're good and close to data, so this is best, so this distance is 0, or you're bad, and then, or you're good and you're not close to the data, and then your goodness is diminished. And you know, you need to have this kind of double distance. So this is, you know, Kullback-Leibler divisions. It's like just distance between the probabilities distribution of sentence generations. You know, like either you're better than this one, and so if you're better than this one and you're far, so I don't trust you. Or if you're better than something really bad, but really bad is also fine, I also don't trust you, right? So this is from the other side, because it's on one side you have minus, another side is plus. So instead of doing the constant optimizer, we kind of modify a little bit of this reward that we'll put to trainings. So instead of this reward that comes from the reward model, from our preference reward model, we'll just, you know, modify a little bit. Good? Questions? Yeah. And so we also didn't expect some benefits of those things. So you can say, like, before FSI defining, we look for this Nash equilibrium, so one policy that will prefer all. Now we look for this regularized, some slightly changed equilibrium. So, you know, is this one something that comes from network minus 2 numbers, minus some numbers plus 2 numbers? But there is, because of this scale, you know, this makes some things convex, and convex functions are nice. And so sometimes, you know, sometimes when you look for Nash equilibrium, it doesn't exist. You know, for example, when I give you an example, I play with him, you know, he plays with her, and like, you know, you don't know who's the winner if there is a circles, right? You don't know what's a Nash equilibrium, or you have like, what is the, you know, rock, paper, scissors, and sometimes there is not unique, sometimes there's multiples, it cannot exist. But if things are convex, there is only one, so it's unique, and you can converge it to it very fast. So we didn't plan on it, and it just happened that because the way how we address this reward hacking problem, it makes things faster, and also, like one technical, very important thing is like you get last iter's convergence, because even Nash had algorithm, and the algorithm was like creating a lot of networks every steps, and the guarantee on the final solution you would have to average all weight possible. So you have to store trillion weight every time step you did something, and this is very costly. And then you have to average it when you start it. Also here, and you have only guarantee on this average. So with this thing, we have actually guarantee on the very last one. We can guarantee the very last one of the training process is good. And we can just output the last one. So, but I still didn't tell you how exactly we train it, right? And actually, how much time I have? Nash already provided the algorithm for this. So we wouldn't even need to do anything, actually. Almost. And so the Nash algorithm, this one, like you want to have this Nash equilibrium. Find a, you know, chatbot that's better than other chatbots, such that, you know, I keep repeating it all the time, but that's what we want to do. And so Nash algorithm, this one. You start with first chatbot, and that's like this SFT, supervised fine-tune policy, after the second phase of training. And then you find one that humans would prefer to it. Well, this is what ChatGPT does, and it stops there. So, but Nash says, well, you don't get equilibrium this way. So they said, well, add this policy to the first one, take these two, so you kind of construct this, Nash call it solution concept, so solutions to the Nash equilibrium, and then find policy that is preferred over both of them. And then you find this policy that preferred to one or two, you put it to the mix, you know, you find third one that's preferred to the all three, and you iterate until things don't change, and you find the final one, it's the weight stop changing, you find a Nash equilibrium. Kind of simple, right? And so we could do that. But the problem is also that you would need to, for every step, you will need to store these trillion parameter networks, and there is not enough space on the planet so far to do that. I have to drink this. This should be time that I get asked questions. So ask or like, oh yes, question, please.
Okay, maybe you would answer this question later, but Nash equilibrium assumes that there is always a winning strategy if we would use a mixed strategies.
Yeah.
So as you are using this algorithm to choose the best LLM,
Yeah.
so you don't assume that they are like mixed strategy.
Oh yeah, I do. There is the Nash LLM that we will get. It will be a mixed strategy.
How do you mix these LLMs?
Next slide.
Okay, next slide.
Yes. Excellent questions. I paid him. Yes, very good, yes. It all makes sense now, right? All right, so we do this algorithm that we had like the, for this 10-year thing that we kind of work independently on. And it's a special algorithm because mirror descent, and it's also kind of like simple to understand, right? You want to find this best response. This is mirror descent algorithm of Arkady Nemirovsky, and the thing is like in every, so the algorithm is, I'll explain it. So you want to find the best possible chatbot in every time step. So what do? You take one, and you try to find, let me take the maximum, in once every step, you try to just maximize this function. So you try to find maximum policy, so maximum chatbot, that will be preferred to the previous one that you had, but you don't go too far, subject to your weights, your neural network weights, or like your probabilities that come up with, more specifically, are not far from the ones from the previous step. From the previous step and some kind of mixed way. So this is like it's mixed from many things. I'll explain this. And so we could just extend this algorithm, but the issue is, this is practical issue, is that like every time step we would need to do this argmax. So every time step we would find a full gradient descent or policy gradient, if you want to say, all the way to find max, and then we have the next one. And then we'll have all the next and the next one. So it's kind of, we would need to kind of train ChatGPT many, like tens of hundreds of thousands times. Very expensive. Right? We cannot do that. We could do that and it would work. Long time to train. So we had to do something else. So there's like, this is things like different from like, let's say, and for this algorithm we have guarantees that it converges super fast to Nash equilibrium. And we can talk over lunch how. But we cannot implement it in this particular way. So we slightly change it, or like we kind of do practical implementation of it. So here, we need to kind of say, well, you need to be not far from the previous one. We're already storing the previous one, it's costly. So there's another way how to say, find something which is not far from the previous one. So instead of going all the way to the argmax, so finding this minimum, what we do, we just do one step. And by taking one step, we don't go too far. Because we only do one step, which only change the weight one step. So instead of doing argmax, we just do one gradient descent step. So we update the weights, just one, right? So you take the gradients, you get this. It's a very similar optimization as ChatGPT is trained. This is this one half that said, well, I want to reduce the variance, and I know that at optimum, it's 50-50. So here I'm just subtracting 50-50 because I have this for free. This is what I explained, this unexpected benefit. And so, but there, we are not optimizing for this preference, right? Because if we optimize for this preference, we would get this reward hacking, right? And we don't like reward hacking. We don't like pizza chatbots. And so so we do this other thing. We do this something that comes up from reward model that we don't train because it's fixed. So we don't need to do gradients over here. Something that was this, KL, and something at some other KL. So we're trying what are we training? We're training this pi, right? This is our chatbots that are improving the weights. So we take gradient of this, then also we need to take gradient of this. But here, since this is some other one, this comparator policy is fixed, so, and this is our supervised string policy, the gradient of this is 0. So this disappears when you take gradients, and this scale stays, and this is what you have here. And actually, nicely surprisingly, this scale is very similar to the one that ChatGPT is trained. So we actually don't need to change the, our structure that it's hyper-optimized to train well that much. We just kind of need to, give this 1/2, changes to the different reward model. But one thing that we need to change is this with 1 and y prime, they cannot no longer be generated from the same policy. So ChatGPT is trained a way that you say, oh, what would you respond to this prompt? You ask twice, you get 2 possible answers because, every time you ask a different answer. Then you ask your reward model which one you prefer between 2 ones, and then you try to make the preferred one more likely, right? It kind of makes sense. So here, we also ask our model, oh, which one do you prefer of the 2, but it's not coming from the same model. The first one is coming from the current model, so our current weights, potentially getting better and better, and we compare it to this mixed policy. We try to mix, so this way kind of represent all other policies. We mix the current policy with this reference policy, with the current chatbot, with the chatbot with strife, or with some proportions. So we kind of take like geometric mixture. So like, let's say if beta is 0.1, then 90% of time we take the current one, and 10% we take the old one. And we mix it this kind of geometric way. Why? Because it works in theory. Second, because this distance between chatbots decomposes because there is some logs, and it nicely decomposes. And finally, because in representation of chatbots and probabilities, we have these logits. So we don't represent the probabilities with things like transformation of probabilities. And so logits, we can just, if you do logits of this one, it's just actually just normal arithmetic average. So like 20% times this, 40% times this. But then our friend will ask, well, how do you get these neural networks? So the way is that you have 2 different policies, 2 different chatbots. How do you mix them, right? Practically, you put the prompt, you do the forward pass of the network, you get the next word or next token prediction for one, next token prediction for the other. Well, you flip a coin, pick either 1 or 2, coin with like 90%, 10%, then say this is my answer, put it in the beginning, do another pass, get another one. So you do it in this auto-regressive way, and this way you kind of mix the policies. 5 minutes, so I just give you the results, and these are not the results on full Gemini, because I'm not allowed to say that. But these are results on a very specific public task called text summarization. You can download the data, try it for yourself. So this is the very simple task. This is the article, give me the summary of it. And then you want to have a chatbot that finds a better summary. And the way how you can prefer one to the other is that, well, which summary is better than the other one? And so these are all possible chatbots that you could try. So this is the one who started it after second phase. This supervised fine-tuning policy. This is what like RLHF, this is the way that ChatGPT is trained. And now you try to see, well, which one the humans prefer. So you can ask humans, which one they prefer. And this is like, for every possible chatbot and the same, you try to find which one is preferred. And then if you look, well, if I have this typical ChatGPT way of training, you said, well, this I started with, and the one that ChatGPT trained, I can find one that 99% is better. And so with other policy, our policy, this one, it's actually not as good. It's less good. So it's not, it's not preferred with respect to this one, this policy. But if you compare this ChatGPT chatbot with any other policies, so this is this one, so it's better than this one. Well, this is if you compare to each other, it's always 50%. Well, that's easy. Well, that's well, we have 50% on diagonal. Sometimes it's better, but sometimes it's worse. I mean, it depends which one is. And we would like to have it to be better all the time, right? So this is what we get for this particular mixture, for this particular mixture policy. It's better than SFT, it's better than RLHF, it's So actually humans prefer it to any other policy possible. And so yeah, I have multiple things because here I mix it with 15%, 25%, oh, I forgot, yeah, so no, it's, I forgot, it's 25, 12, 12.5, 25, 37.5, and so on. And so actually it's nice to see that a lot of these mixtures actually are already good. So for a lot of mixture, you could find something better than ChatGPT of weight training. So at least for these 4 mixtures, so it's not that sensitive to hyperparameters. Because Wojtek wanted to ask me, like, how sensitive to hyperparameters? So this is the answer. We have very little time for questions and we want to eat. So I'll ask question to myself. And so the stuff that I want to see, like, yes, if you find one chatbot is better than this one, you still should do RLHF or ChatGPT way of training. But if you want to find something that's preferred to any other ones, you should switch to this way of training, to this Nash-LLM training. This is also a very interesting point because this is, you don't mix the policy, the mixture is equal to 0. So you don't mix anything. And this is also very known algorithm called self-play. This is like AlphaGo training. You play always with each other. It doesn't do as good as a mixing. It does pretty well, practically. We don't have any proof if it works well, because we have proof for any mixture that is non-zero, like non-zero. So it's also kind of open question. Can we prove something like how this self-play, which is very known, common, basic algorithm from game theory, you just play with yourself and you get better. And this is, that's like AlphaGo style of training. But at least practically, it's not right now that performs the best. So maybe that's why. Maybe this doesn't go well. But it's kind of interesting open question. What would self-play do? And there are some other approximations. This Nash way of style of training when you average a lot of weights. So we tried them. They didn't perform that well because it's also averaging weights doesn't necessarily average probabilities. So at the end, the stuff that we use at the end is just like this mixture. The best mixture that worked, the best proportion that worked was 12.5%. And that's it. Thank you.
Okay, thank you very much. Yeah, we have the first question.
Okay, so thank you for this amazing talk. And I may be totally wrong, so just correct me. But if you could come back to the slide where you defined like the combination of those models. Oh, I think we missed it a bit. Yeah, right here. So like when you presented it, it was a bit similar to an idea of a min teacher from semi-supervised learning, and there you just average with the exponential moving average the weights, and you perform the labeling. Could you comment on the differences between those two methods and how are they similar?
Absolutely. So these are the columns on the right that didn't perform as well, practically. So of course we tried it. Why? Because that was kind of obvious, and this is what we did in maybe some of the work that I work on, like BYOL. It's also very similar to min teacher when you average the weights. Because also, this algorithm for self-supervised learning is also coming from game theory, and there it works. And so of course we tried it here because we know how to do that, and you just repeat. If you're old, you forget stuff, and so we tried first, and it didn't work. And why? And so I tried to see like all the other articles, like because this exponential moving average is kind of very common in deep learning, and it works quite well. So why it doesn't work here? These are ideas, I don't know, it's an answer, but these are my ideas why it probably doesn't work well. One thing is that, we would like to average probabilities, so outputs of the network. It's very difficult to average the output. So instead of, it's much cheaper to average the weights, because to average the output, we need to store them all the weights, and then average, compute outputs all the weights, and so we do approximation. So averaging weights is only approximation of what we want. This is like first thing which probably doesn't work well. But this is also true in the bio, and there it works. So there's maybe another thing that works. The one thing that's like, this is game theory stuff, which is not classification or like kind of prediction stuff. This is, so what we're having is like probability. So at the end what we store, it's with probability the next token predictions, and we store them as a logits, right? So this kind of nonlinear transformation, simple but nonlinear. And so that's again thing, right? Like you average weight, you know, you cannot reverse expectation on log because it's nonlinear. Somehow logit is nonlinear. So it's wrong to do it. And so that's why, because you cannot, you know, how it's called, commute expectation, like the sum, you cannot commute sum and log. That's why, and that's what you kind of assuming you can, then it doesn't work. So this system, we still wanted to try it because sometimes, you know, this deep learning, right? Sometimes we think that doesn't make sense, just works better. So we did try it, and that's what. Does that answer the question? Yeah, thank you.
Thank you. So now you compare just pair of options. And is it possible to somehow generalize to have more options at specific moment? Would it be beneficial? And
yeah, it's possible, like kind of multi-rank classification. Like we could do it algorithmically. We have no idea how to prove things for it. So I didn't like go over the proof, but we have a guarantee at the end that actually like, learns kind of super fast, like the linear convergence. We don't have idea because we kind of, there's several things that like so game theory is very difficult. And somehow, here it became easy. It's very weird, right? Like it's very, like, and the reason why it became easy is that like you have deterministic things, you know, like when you choose next word, next token, you get this next token. So it's deterministic. While in game theory, when you play poker card, you don't know what you get back. You know, it's like sometimes by chance. One thing is deterministic. Another, it's they're symmetric. So like preference of one is 1 minus preference 0. When you go to this multi, it's no longer symmetric. Well, it's difficult what does it mean to define a symmetry. So there is a trivial way which could do it. You can always set 1 versus everything else. And then it would work, but you know, it's kind of cumbersome and you need to have multiple reward, multiple stuff, right? And the third one, why these things make it easier for proving a game theory stuff, because actually the guarantee is actually very, very easy to show, is because of this convexity unique equilibrium. So, you know, there's some kind of variential equations that like optimally something that makes something very, very simple. So because we are, luckily for this 2024 problem of training large language models, luckily this is from game theory perspective is kind of easy. And so because of this kind of easiness, we were able to have these guarantees. And one thing that was necessary to have it is that you compare only option 1 versus option 2, and not the option 1. Practically, it's possible to, you know, have the network that, you know, you put in a lot of options, you train it, it's just a network, right? Deep learning, it learns everything, you know. It can work. We did not try it that particular way. We tried it like we tried it like doing kind of 1 versus all. This works fine for some small things, not trying like big models for some different policies. But it's not something that that we explored really well, and of course it will be useful. And then the one reason we didn't try it, like of course we are lazy is the real reason, but the reason is that you would need to have this data from people. So right now there are these companies that provide the data, and you know, the more answers you have, like it's more difficult, you know, for people to decide which one is better. Or we will need to say, oh, here's the, you know, here are 100 answer methods. Rank me which one you like. It's just more difficult for you even to do much consuming. I would probably have to pay you more for doing that. And that's why a lot of times we just compare the two, like in clinical trials, right? We usually do A/B testing, right? Why we don't do A/B testing for multiple things, right? It's like it's very practical thing. It's like it's much easier to say like do green button on red button rather than give you all the colors of universe and pick one. Yeah, so that's why.
Thank you very much.
They want to eat.
Yeah, okay, so we can conclude this session because we are already a little bit late. So let's make the final round of applause for Michal. And enjoy your lunch.